Where did we come from? As far as we know, it all started with a singularity in the middle of nowhere that expanded. The most popular idea we have of this is a kind of explosion, a boom. And then, from this boom, in a time interval so small that we can't even conceive it, our universe emerged. Everything we know today began at the same instant. Space, time, the four forces of nature, particles, and light elements like hydrogen. And after hundreds of millions of years, still as a consequence of that very massive boom, the very first stars and galaxies emerged. A few more billion years passed and we are on a planet orbiting a star that resides in a galaxy. That's it, the story of the universe in less than a minute. This is a simplified way of talking about one of the models of how the universe evolved to what it is today, which is the Big Bang Theory. But if we want to answer the question I asked at the beginning of the video, where did we come from, then I have some news to share with you. The Big Bang Theory is the scientific community's favorite model to answer this question. And the reason it is the favorite is simple. Observations agree with the theoretical models predicted by the Big Bang, but things are not as simple and straightforward as they appear. Models and observations are part of a field of science called cosmology, which is an area that tries to understand the origin and evolution of the universe. However, cosmology deals with a very complex challenge. We have only one universe to study. In science, to prove a model, we need observations, and these observations are made through experiments that are repeated multiple times, or by observing some phenomenon that repeats. As for cosmology, things get complicated because it is impossible to simply create a universe in a laboratory to test each cosmological model, and we also have no way to observe another universe to see if something changes from one to another. And that is why cosmology depends on observations of the past of a single universe, which is ours. This makes it necessary to make observations of our universe at different stages from when it was very young to the present day. And for that, we need better data, as that's the only way we will be able to get the details of the chronology from the moment of the Big Bang. And we can only do this using advanced technologies, such as increasingly sensitive telescopes that reach regions ever farther away, in the order of billions of light years from here. A light year is a curious measure because it is a measure of distance, but at the same time it gives us a notion of time. When we say that something is billions of years away in distance, it also means that what we are seeing is the light that was emitted billions of years ago in the past. And that is exactly why we need more powerful telescopes, because with them we can see farther, and as a consequence we can see the past better. And an example is the construction and launch of the Hubble telescope in the 90s. The main mission of the Hubble telescope was to observe more distant regions to estimate the rate of expansion of the universe. Hubble was responsible for some of the most beautiful images in human history, but it was only in our current decade that cosmology managed to take a step further with the James Webb Space Telescope. The James Webb was conceived as a revolutionary telescope with the goal of answering questions like when did the first stars form? How did galaxies emerge? How did supermassive black holes come into existence? And for that, James Webb had to observe a past of the universe that had never been observed before, and I'm talking about just a few 100 million years after the Big Bang. And I know you must be thinking that this is still a lot of time, and me using it just to talk about millions of years seems like a mistake. But don't forget that we are talking about the universe. And it has an estimated age of 13.7 billion years. Hundreds of millions of years are a blink of an eye when we talk about the universe. And besides, there is another reason why this period is of interest to researchers. Within cosmology, this time exactly matches the era when we exactly expect the first stars and galaxies to have emerged. And that's why the whole idea behind the James Webb was exciting from the beginning, to answer these questions. And so far, the James Webb has already brought various results during these few years it has been active. And one of these results happened during the first observations, in July 2022. More specifically, the first deep field image from James Webb. Some astronomers began to notice a problem right in that first image, something that was not expected by our theory. The galaxies were much larger than we actually expected them to be. This creates a significant problem because in our most accepted model of galaxy evolution, there wouldn't be time for them to have reached those sizes. So, while this raised a question mark for astronomers, it didn't take long for other people to start claiming that the Big Bang theory was wrong. If the galaxies didn't have time to become so large, considering that the universe was young, then the universe must be much older than we thought. So the Big Bang theory should be wrong. And that was basically the line of reasoning that many followed, which ended up going viral on the internet. It is not uncommon even today to find people claiming that the James Webb proved that the Big Bang didn't happen. But is that really what happened? Did the James Webb prove that the Big Bang didn't happen? Or is there a better explanation for these results that have indeed left astronomers with a problem on their hands? Spoiler alert! Maybe some things in astronomy will change completely, but not in the way you're thinking right now. Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video. To begin with, the Big Bang Theory is in fact more of a popular name that caught on, like the God particle. In reality, the Big Bang Theory is associated with a mathematical model called Lambda-CDM. We can translate Lambda-CDM as follows. Lambda is the Greek letter, and it represents the cosmological constant, and CDM is the abbreviation for cold dark matter. The cosmological constant is a parameter that is related to the expansion of the universe, and remember that the expansion of the universe is related to dark energy. So, calculating the cosmological constant is often associated with the study of dark energy. The constant is present in Einstein's general relativity equations, and these equations are used to describe how spacetime behaves, including its expansion. And I know that whenever we talk about these equations, we talk about spacetime distortion like black holes. But the importance of these equations goes much further, even to describe the universe as a whole. These equations are not exactly simple, and they include some parameters, among them the cosmological constant. Originally, it was introduced by Albert Einstein himself to counterbalance the effect of gravity in the equations. But he discarded this idea a few years later, assuming that the cosmological constant was wrong and it wouldn't make sense to include it. And at the end of the last century came the proof that the universe is not only expanding, but it is expanding in an accelerated manner. And this acceleration would be caused by a repulsive effect, opposite to gravity, just as Einstein thought at the beginning of the last century when he used the cosmological constant. And with that, astronomers reintroduced the constant into the equations. And that's where the joke comes from that even when Einstein is wrong, he's right. The cold dark matter part of the name relates to dark matter. In this model, dark matter is actually non-collisional, with low velocities, or if you prefer in physics jargon, something cold. The Lambda-CDM model has successfully predicted various discoveries. Some examples include the cosmic microwave background radiation, the amount of elements like hydrogen and helium, and the very acceleration of the expansion of the universe. Additionally, the distribution of galaxies in the universe, which we call the large-scale structure, was also predicted by this model. That's why the Lambda-CDM is one of the favorite models among cosmologists and astronomers. It has a track record of consistently successful predictions and is continually and thoroughly tested with increasingly detailed observations. Because of this, the Lambda-CDM is the preferred model to explain the origin and evolution of the universe. But what kind of evolution does the model predict? Let's suppose I show you a balloon that is already a bit inflated and I continue to fill it. You observe it expanding, and if you imagine its past, you assume that at some point in the past it was empty. You don't even need to have seen it empty to draw this conclusion. When you observe it filling up and expanding, you automatically rewind in your head and come to this conclusion. For the Lambda-CDM, the universe would be like a balloon. If we see it expanding and we know that in the past the universe was smaller, then we can assume that at some point it was so small, but so small, that it was just a singularity, a point in the middle of nowhere. And from this point, all the expansion that we see today would have started. This is the famous explosion that was named the Big Bang. In those first moments after the Big Bang, the universe was hot enough for everything to be in the form of plasma. Plasma is a state of matter where the temperatures are high enough to ionize the elements. Few people know, but the universe had two accelerations, and the first one happened in those initial moments and led to the name inflation. During inflation, the universe went from the size of an orange to the size of a galaxy in an incredibly short period between 10 to the power of minus 32 and 10 to the power of minus 33 seconds. If you were observing the universe at that time, you wouldn't even be able to notice the moment it went from the size of an orange to the size of a galaxy. For you, it would have been instantaneous. This is the level of inflation. And after inflation, the universe continued expanding, and with that, it started cooling down and no longer had temperatures high enough to ionize the elements. In this way, from the first minutes to the first 300,000 years, atoms were formed. Initially, neutral hydrogen was formed and then helium atoms. The first molecules, which were mainly composed of hydrogen and/or helium, such as molecular hydrogen, also began to form at this time. And between 300,000 and 400,000 years later, we entered the Dark Ages. There wasn't exactly a source of light. That's because most of the elements and molecules were already in their neutral form, so there wasn't any phenomenon producing photons. the universe was dark. But as it reached its first millions of years, we then expect that stars would have started to form. They would gradually form by the collapse of cold clouds of molecular hydrogen. And these stars would be the first source of light that the universe would see in a long time. And then larger structures like galaxies also began to form. At the end of the Dark Ages, around 1 billion years after the Big Bang, the era of stars begins, which is the era we live in today in the universe. As the name itself suggests, it is an era dominated by star formation. But I want to go back a bit further in this story because our focus here is precisely the Dark Ages. I need to emphasize that there are observations that agree with this description I just made of the evolution of the universe. And the mathematical model is embedded in the Lambda-CDM. But perhaps the biggest source of problems here is precisely the Dark Ages. The first problem arises because we are talking about a very ancient time in the universe, which until recently we did not even have enough technology to observe. The second problem arises because it seems that many of the open questions in astronomy depend precisely on what was happening during that time. Two of them being how the first stars came into existence and how the first galaxies emerged. The formation of a galaxy is an enigma within astronomy. Various models have tried to explain how it happened, but the lack of observations left all these models with a question mark at the end. They formed through a hierarchical model, where smaller structures merged to form the galaxy, or through a monolithic model, where the galaxy formed all at once right after the collapse of a significantly massive gas cloud. Was it the supermassive black hole that was pulling in matter and forming small blocks of stars, or was the galaxy already formed and then the black hole was just pushed there through some, gravitational push? This is like the astronomical version of the question, which came first, the chicken or the egg? Which came first, the black hole or the galaxy? The Hubble telescope itself was used in an attempt to observe this era in the universe. But when Hubble observed ancient galaxies in the universe, it found small and not very massive galaxies. These galaxies agreed better with the hierarchical model of galaxy formation. However, the Hubble was not a telescope focused on observing very distant regions. It was not built with that purpose in mind. So there was no way to know if what they were observing was really proof that the hierarchical model was correct. Therefore, a new telescope was needed with enough advanced technology to see as far as possible, with the goal of observing these first galaxies and the first stars to finally put an end to the discussion of how galaxies formed, and thus the idea of the James Webb Space Telescope was born. The James Webb Space Telescope is considered the successor to the Hubble telescope, but it is important to make clear that they have differences between them and different objectives. So this statement is not very accurate. The first difference is that the James Webb observes in infrared wavelengths. The Hubble observes in the optical and only a small region in the infrared. Another difference is that the James Webb aims to observe the first light of the universe, which is precisely this period in the Dark Ages between 100 to 400 million years after the Big Bang. The Hubble aimed to measure the rate of expansion of the universe by observing different epochs of our universe. The James Webb has approximately 6 times more light capturing area than the Hubble telescope. This gives it greater sensitivity and higher quality in total. Because by capturing more photons, more additional details are captured in the objects being observed. But undoubtedly the big difference is the range of light that the James Webb observes. And this range allows it to see even farther than any other telescope. To be more specific, the James Webb observes in wavelengths between 600 and 28,500 nanometers. And these wavelengths fit into the region of the spectrum called infrared. You might be wondering, why observe in the infrared? Why not in the optical or even in more energetic wavelengths like X-ray or ultraviolet, which would make sense if we think that we are talking about objects with quite energetic emissions? The reason is the Doppler effect. This is the same effect that causes the frequency of an ambulance to change depending on the speed at which it approaches and moves away. In the universe, there is also a similar effect known as the cosmological Doppler effect. When a distant galaxy or star emits photons, they will travel through the fabric of space-time until they are absorbed by something. As they travel, the universe is expanding and the wavelength of the photon is stretched along with it. To make it easier, imagine the photon as a spring. As the spring moves, it gets slightly stretched along with space-time, which acts like an elastic spring being pulled. And because of this effect, if that photon was emitted at a short wavelength, it will be slightly stretched, resulting in a longer wavelength. The farther the source is from us, the more the cosmological Doppler effect will cause the photon to suffer. And we can even calculate the distance at which the photon was emitted using this equation. Z is called redshift. It quantifies how stretched the wavelength has been, and from it, you can obtain the distance to the image. In the case of these first galaxies, the photons traveled long enough to be redshifted to wavelengths that fall in the infrared. That's why we indeed need to use tools that observe specifically in the infrared. Otherwise, we won't be able to see that era. And we also need tools that are sensitive, because we are talking about objects that are very, very far away. So, there are few photons that reach us. And this is the great revolution of the James Webb compared to other telescopes. The ability to observe in these wavelengths and have a larger collecting area. James Webb was launched on the Ariane 5 rocket on December 25, 2021. And I think this was probably the most important milestone in astronomy this century so far. 6 months after the launch, James Webb had already captured its first images, which were released in July 2022. In total, 4 images and a spectrum were released by NASA during a live event on July 12th. But the day before, the White House had already released the first deep field image from James Webb. It didn't take long for astronomers to dive into the first images for thorough analysis. And soon they found galaxies that broke the record for the most distant objects observed in the very first photo. One of the several articles published, known as Panic at the Disks, I think I know what kind of music the authors like, was one of the first to do this. It even found some of these galaxies. Other authors and groups also reached similar conclusions, but as nothing is perfect, a problem soon arose. When they calculated the mass of these galaxies, they realized that they were much larger and more massive than expected by the theory. And they had more complex structures than expected for such young galaxies, which, in theory, had just formed. They already had the size, mass, and structure of galaxies that are, in fact, much older. They were supposed to be small. They were supposed to be not very massive. They were also supposed to be unstructured, as Hubble had given the impression. The problem is, if they formed slowly with small structures coming together over billions of years, how were they already large when the universe was so young? The universe hadn't even reached 1 billion years old, so there wasn't enough time for such large structures to form. In short, the galaxies were much more advanced according to our understanding of galaxy evolution. They could not have formed in just a few million years, and that's when astronomers realized something was wrong, and the controversy began. At the time, Nature magazine invited astrophysicist Alison Kirkpatrick from the University of Kansas to talk about James Webb's discoveries. And during that interview, the astrophysicist referred to these discoveries with the following phrase: "I'm awake at 3 a.m. wondering if all the work I have done is wrong." This was enough for some people to actually take that phrase and use it to justify that the Big Bang was a lie. And in a few days, this spread across the internet, and the headlines generally read, "James Webb proves that the Big Bang never happened." And the argument that all these articles use is that the existence of these galaxies at that time does not align with the age of the universe. For them, the universe would be older than expected, so the Big Bang couldn't have happened. And this became so famous on the internet that even today you see people using this argument whenever someone talks about the Big Bang. But is that really what happened? Did James Webb prove that the Big Bang theory and everything we know about the evolution of the universe is wrong? Kirkpatrick herself came forward to say that the phrase she used in the journal Nature had nothing to do with the Big Bang. She believed in the Big Bang theory as the best explanation for the origin of the universe. So what is the reason for her statement, and where did all this chaos come from? The truth is that yes, the galaxies are more massive than expected by the theory. So there are theories that will need to be revised, but it is not the Big Bang theory. If you paid attention to the video, you must have noticed that James Webb was launched with a series of open questions, and one of them is about the formation of galaxies. Before James Webb, no telescope had the technology to observe such a distant past of the universe. The few observations that existed coming from Hubble were not of good quality, and it was impossible to assert anything about them. It was not possible to settle on one of the galaxy formation theories with the technology prior to James Webb. And this question was one of the missions of James Webb. Think about it. If it was built and launched with billions of dollars invested, it's because this question was still open and needed to be resolved. It didn't make much sense to launch something with a question that had already been answered. And what James Webb found was precisely that our idea of galaxy formation was not correct. The point I want you to pay attention to here is the following. The formation of galaxies has always been an open question in astronomy. It wasn't James Webb that did this. The fact that James Webb showed that what we believed was wrong only indicates that we need to review galaxy formation models. And that is what astrophysicist Kirkpatrick meant when she said that everything she had learned was wrong. This is not even that surprising for astronomers who have always had their doubts about the galaxy formation model. James Webb has only shown with these observations that we need to rethink these models. And that's how science has always worked. We create a model and test it with observations. If the observation doesn't match, we redo the model. This is not something new. It has always happened in science and always will. This is the beauty of the scientific method. Basically, we had something with only a vague idea of how it worked, the formation of galaxies. And then James Webb came along and showed that things weren't quite as we thought. If the theory of galaxy formation is wrong, then can't the Big Bang theory also be wrong? And you're absolutely right to think that way because we're talking about science. Statements should be questioned, and I am very happy that you asked yourself this question. And I want to show you another incredible side of science, which is why some models are more accepted than others. The first thing is that the Big Bang model is the one that most agrees with the observations we have. But that doesn't mean the matter is settled once and for all. The only thing is that nothing so far has proven to be a better model than the Big Bang to explain these observations. There isn't even any strong evidence to prove that the Big Bang didn't happen. And here we come to that famous phrase by Carl Sagan, extraordinary claims require extraordinary evidence. So, to say that the Big Bang happened or didn't happen, which is an extremely extraordinary claim, we need to have evidence to confirm it. One piece of evidence is not enough. We need to have several that have been tested multiple times by several different groups using various techniques, and the statement, the Big Bang happened, fits precisely at this point. She has a series of observations with different groups, in different years, using different methods that are always redone. And they all indicate that the Big Bang theory is the best explanation for the origin of the universe. The main observation is the cosmic microwave background radiation predicted by the Lambda-CDM model. And other observations include temperature and disturbances, which are also predicted by the model. The observations from Hubble and other telescopes that can map large-scale structures also agree with this very statement. There are various ways to calculate the expansion rate of the universe, and all of them agree with the mathematical model that describes the Big Bang. In other words, there are indeed a series of observations in different ways that have actually been redone multiple times and agree with the Big Bang. James Webb, on the other hand, focuses in just one way, which is observed infrared. So, even if it had proven something contrary, it still wouldn't be enough to go against all these other observations. But it is important to make one thing extremely clear. The data from James Webb did not prove anything against the Big Bang. They only proved something wrong against our idea of galaxy formation. And of course, there are claims and experiments that try to show that the Big Bang model is wrong. However, these experiments do not have enough evidence to support the claims that the Big Bang is wrong. Taking our own theory of galaxy formation that we had in mind, there were only a few pieces of evidence which were low-quality images from Hubble. The Big Bang model has much more supporting evidence than the galaxy formation model did. And I think this is a perfect example of how science works and also how fake news can easily spread on the internet. James Webb is showing us the young universe in more incredible detail for the first time in history. It will answer questions that still have no answers and even help us create models of things we had no idea existed in the universe. And that's exactly what it did. It gave us observations of something we never exactly knew how it exactly worked, because we barely had any observations. The lesson is the same one our mother tells us. Don't believe everything you read on the internet and always seek reliable references. For example, the references for this video are always in the description like every other video from Scienceverse. Moreover, it is a valuable lesson to understand how science works, and that theories are not just theories in the same sense we use in everyday life. Theory holds weight within science and is something that has already been tested with observations and has strong evidence in its favor. Always keep in mind when you read that something has disproved a concept or a theory in science. The most important lesson from this video is what Carl Sagan said. Extraordinary claims require extraordinary evidence. Thank you very much, and see you next time.